So, torque and vectors. Which way is the thing spinning? And we've already talked about the right-hand rule, yes? The physics gang sign? Wait, shut the door. I'm going to be saying these words. I don't want an administrator freaking out. All right, so all right, we'll make that guy solid. And that guy, there we go. So which way is the thing spinning? What we need is some way so that we can agree on which way this guy is spinning, no matter where I'm standing. So if I'm standing back here and I say, no, it's spinning clockwise, and you guys say, no, it's counterclockwise, we need some way to resolve this, and that's the right-hand rule. All right? So, the modified right-hand rule that we're talking about is you're going to take your fingers and they're going to curl in the direction of the spin, and then your thumb then points along the axis of rotation. All right, so from the axis, fingers point out. That's the beginning of the right-hand rule like we've done before. And then notice your palm is going to point in the direction of the curl, so your fingers can curl in the direction of the thing that is actually spinning. And then your thumb is going to point in a particular direction along the axis. That direction that your thumb points along the axis is the rotational vector that we're going to use. So, yeah, it's spinning in that direction, but then we're going to say that's the vector. The vector is along the axis, all right? Angular vectors point along axis of rotation by right-hand rule. So you're going to use the right-hand rule. So from the axis out to the object, or the rim of the object, if we're going to talk about a solid extended object. So there's R. And then your palm is going to point in the direction of the spin. And your fingers are going to be able to curl in there. And again, right-hand rule, not the left-hand rule. So you have to use your right hand. If you use your left hand, you're wrong. We live in a right-handed universe, not a left-handed universe. So fingers, palm, thumb. And the thumb is going to tell you what direction the vector is pointing in. So let's go back to this guy, and I spin this guy like this, and then you do the right-hand rule for this guy. In which way does your thumb point? Whoa, let's not do it that way because then things start flying off. All right. If I'm doing this way, which way does your thumb end up pointing? Towards the back of the room, yes? And I need to switch hands because I can't do the right-hand rule with my left hand. So if I'm doing this and I pick the stopper up at the top, so I'm going to go from the center to the stopper and my fingers point up, and my palm is going to point towards the hallway when it's at the top there so my fingers can curl around. And my thumb also points towards the back of the room, just like yours does. We can agree on this. All right? We finally agree on something. It's a magical day. All right. Next thing. Now that we're done with that, let's talk about torque and rotation now. Torque and
I said axis.
I know, I heard it. He's the one with wax in his ears. All right, torque and Newton's second law. So remember, F equals ma. That's Newton's second law, yes? Now let's grab this thing and spin it around. Well, if we're going to spin it around, that means it's torque. And I'm going to grab it up here, distance r away from the axis, and force this thing to spin. Which means, so let's play with this equation. We'll do, the x is the cross product. Remember that? We have two kinds of multiplication here. We've got dot product, where I'm going to push something in a straight line, or I've got the cross product where I'm going to cause the thing to rotate. So this is, I'm going to cause the thing to rotate by grabbing it and spinning it around the axis. In order to do that, I have to grab it a distance r away from the axis, and torque is r cross f. So I want to make sure that the r is on this side. Because if I just do fr on the other side, that's something else. And we're not doing that. Hey, we talked about the relationship between linear acceleration and angular acceleration the other day, right? So A equals R alpha, remember that? Vaguely, a little bit, if you were here and taking notes. So let's substitute that puppy into there. So we're going to have R cross F equals R cross MR alpha. All right, so let's deal with this cross product thing. So if I grab this thing and I yank it, what's the angle between the R and the F as long as the F is tangent to the circle? 90 degrees, yes? So that's going to be all of R times all of F because they are 100% perpendicular, right? Okay, how about the tangential acceleration of that point that I grabbed? How does that relate to R? Okay, so I grabbed this guy and I yanked it to the side, so this point is also going to accelerate tangent to the circle. How does that relate to R? Also 90 degrees? All right, so we've dealt with the cross product. So these two cross products, we actually don't even need them anymore because so cross if F tangent, then R and F are perpendicular, and we don't need to worry about the cross product because we did the cross product thing, and now we're just going to have multiplied. Just the number of R and the number of F, and we throw them into the calculator, and out pops the answer. All right, really hard question. R times R today is R squared. So I'm going to have RF equals MR squared alpha. That should begin to look like something that we've been playing with for the last 2 days. Which is? That's rotational inertia. That's your most basic form of rotational inertia. So this guy, so I grabbed that point, and keep in mind, I'm only grabbing one point. I'm not talking about the whole circle thing. I'm just this point. I've grabbed that point. I'm making that point rotate around the circle. So that puppy's eye. RF should also look like something. R cross F has another name. Title of today's notes? Yeah, torque. All right, so torque equals I alpha. So I just turned F equals MA equals torque equals I alpha in just multiplying by R. It's a fancy seesaw. Greek letter tau. So there's the other Greek letter tau that often gets, or there's another like hangman's noose thing. You ever play hangman? There you go. Capital tau. This one? Yeah, well, I like that one because it makes me think of a seesaw, which is where we start with torque. All right, so this guy is Newton's second law in rotation. Let's move this puppy over a little bit. There we go. Yeah, all right, so we had K equals 1/2 mv squared. That then got turned into Ke equals 1/2 I omega squared. And what you should notice is that we have mass turns into rotational inertia, and linear speed turns into angular speed. And now we have F equals ma, torque equals I alpha. And all I did was trade out the linear quantities for the rotational quantities. It's an analogy that works very, very well. And we did the same thing in kinematics too. All the V's turn into omegas, and the A's into alphas, and the S's into thetas. And there's no such thing as rotational time, fortunately. That would be a mess. I'm glad we don't have to have rotational time. All right. What if we do work? Can we do that for work also? Does this work? All right, what if we're causing the thing to spin around a circle? So let's back up to our circle, and we'll go like that. Here's theta. That was the distance. Hey, the relationship between the distance s around the circle and the theta of the angular displacement is r times theta is s. Yeah, remember that? So if we come into here and we say, hey, by the way, r theta, and we're only keeping f perpendicular to r. We're not doing anything where f is not perpendicular to r right now, because that would be a mess. Then we're going to have f times r times, hey, what's f times r? or R times F. Their torque. So work equals torque times theta. So R times F, well, that's going to be torque, and theta is just theta. We can take all the linear things and turn them into the rotational equivalents by saying, hey, this thing turned into angular quantity is that symbol, but it's the same basic idea. All right, let's take a look at my, let's see here, where is it? This one. Why does it what? R disappears inside. Torque is R times F. So the R has disappeared inside the torque. It's being hidden. Good question. All right, so let's zoom in on what's going to become my demo here. There we go. All right, so previously I had said that pulleys, we're going to pretend the pulleys don't need to be rotated in order to rotate. And then I said, well, actually they do. And Jake started just like, dear God, please no. All right, so I have here a spool that used to have some kind of alarm wire on it. So we have a hoop and a disc and another disc. This is a composite object. So we've got mr squared with one kind of m and one r, and then this 1/2 mr squared and this 1/2 mr squared. All right, and I've got this short mass here, and this mass is on a radius there. So this guy's going to fall and make that guy spin. Now, what if, wait a second, what if I take this guy and I just let go? What's the acceleration? Pretty much gravity, yes? So if I take this guy and I just let it go, it's going to be gravity. Now, what if I put this guy on, hook this guy on here with a string, and I let it go? Is the acceleration still going to be gravity? No, because some of that force isn't just on this guy. It's going to be transferred to this guy to force this guy to spin. And this guy's not actually falling. This guy's spinning. So when I let this guy go, let's get you out so maybe you don't hit the table. All right, as opposed to a lot faster when there's no string. Yeah? All right, so let's take a look at that guy, except I don't want to use the weird spool thing in my calculation. Let's do that one. There we go. Yeah, let's just use a disk. Let's pretend the whole thing is a disk. Let's here, consider block M attached by string to a disk pulley of mass M and radius R. And what we're going to do is we're going to let the mass fall, and we need to do this again. So notice that, so this guy is going to move linearly, this guy is going to move angularly, and they are tied together by the string. Now what we're going to have to do is we're going to have a rotational thing, and we're going to have a linear equation, a rotational equation, a linear equation, and then we're going to have to tie them together mathematically. Hey, derive expression for linear acceleration of a block. And that is going to be tied to, mathematically, derive expression for angular acceleration of pulley. Because they're happening at the same time. And the one thing is happening while the other thing is also happening. And they're related to each other. So, oh, by the way, this only works if the string doesn't slip. As soon as the string slips, we can't really do this. It falls apart. So let's not consider that. So let's see here. The linear acceleration of the block is going to be from this column. Sigma F equals MA. And you know what? While we're at it, we should probably have a picture here. Here's this guy. And, oh, wait, I think I had it on the other side. So we got this guy, and then that, and M, and R. So if we're going to think about this in terms of forces, we need to draw a free body diagram of that guy, and we need to draw a free body diagram of that guy. So everything turns into a dot. mg down, ft up. We've seen that before. That's not new. But for the pulley, The only thing it sees is tension. The pulley does not see the actual weight of the block that's falling. The pulley only sees the tension in the block, which is not the same as the weight as soon as the weight is accelerating. If the weight is accelerating, that means the tension is losing the battle, and it's smaller than the weight. All right, so we're going to have, which way do you want to do positives? Do you want to do in the direction of the spin is positive? Because if we do that, then everything turns out to be pretty, and we don't have extra negatives floating around. So if we say in the direction of the spin is positive, then that means that's positive. Down is positive. If we do it the other way, then we're going to have an extra negative floating around that's going to cancel out anyway. So how about we skip that part, and then we're going to have mg minus ft equals ma. Not that bad, right? Minor problem, though. We don't know ft, and we don't know a. Bother. So next equation, we got to go to the rotation. Now we got to look at this guy. So for this guy, since this guy is spinning, we're going to have to add up the torques that cause the thing to spin. And we only have one torque on this. That's that tension in the string. So we're going to have R cross Ft equals, I said disk, right? Yes, disk. 1/2 little m R squared alpha. So I'm taking that and I'm substituting in specifics. Now, as long as the string doesn't slip, if string not slip, we get to do that. If and only if the string does not slip, then we get to say that the tension, that the linear acceleration and the angular acceleration are tied together by the radius r. Ooh, hey, look at that. I've got an r and an alpha here, r and an alpha. Yes? So substitute. Also, I have another r here and an r there. So kill one of those guys. Because I've got that. So I just made a substitution and a cancellation all at once. And that ugly thing suddenly got a lot less ugly. And now I have an expression for tension in terms of the acceleration. Oh, goody. So guess what I get to do now? Substitute back into the original guy. Oh, goody. I have my second equation for my two variables. And I got rid of my third variable that appeared magically. And so I'm going to substitute that guy into here. So I'm going to have big mg minus 1/2, and that's mass of the pulley, A equals big M, A. So a little bit of algebra now. Rearrange, divide. You're going to come over here. So mg is equal to m plus 1/2 of the pulley, A. And so the linear acceleration is going to be the weight of the guy modified by the fact that I've tied it to a pulley. Now, quick and dirty question. No, quick and dirty check for did I make a brain fart? If I cut the string, the mass is, the hanger is no longer attached to the pulley, right? So the acceleration should be gravity. Okay, now mathematically, what does that look like? If I cut the string mathematically, what happens to my equation? What? No, not the entire denominator, though. Something in the denominator. M of what? I've got two M's here. The small m, because that's the pulley. So if I eliminate the pulley by cutting the string, now I have weight divided by mass. Well, weight divided by mass today is gravity. Okay, good. So then the acceleration turns into... Are we out of time already? Not cool. All right, then the acceleration turns back into gravity, and we discovered that we did not make any brain farts. All right, let's pick up where we left off yesterday, I think. I think we got down to here, and I said something about cutting the string, right? Cut the string and remove the pulley. So then we have m times g divided by m, and they cancel out, and then you just have the acceleration of the block, because this is the acceleration of the block. So the acceleration of the block is reduced by the fact that now we have to cause the pulley to accelerate. But if the pulley's a disc, we get a 1/2 m. If the pulley's a hoop, we get something else. If the pulley is composite, we get something else. All right? So, number one, as you saw yesterday, the acceleration of the block was less than gravity when I had it on the string, and it was equal to gravity when I didn't have it on the string. So our quick check for do I have a brain fart on this, that doesn't mean that this is right. That just means that it's not definitely wrong. If you ever end up with acceleration is bigger than gravity, that's a problem. You should never end up with acceleration is bigger than gravity if you're dropping something. Like if you end up with a minus sign here, that should tell you that you goofed. All right. B, angular acceleration of the pulley. Well, I have linear acceleration, and they're tied together, and there's no slippage of the string. You don't want to need string slipping. If the string slips, then we've got other problems, and we'll get to that later, probably after Christmas break. So we're going to take this answer and just divide by r. So we'll have mg, and then m plus 1/2 other m r. There you go. That's the angular acceleration of the pulley. Notice that its angular acceleration depends on how big it is. But the linear acceleration doesn't depend on how big the pulley is. It depends on how massive the pulley is. The more massive the pulley, the slower the thing's going to fall. And then as we've done, remember the Atwood's machines, and we talked about the Atwood's machines. We zoomed out and we looked at everything all together to get the acceleration, which is what we had to do here. We had to look at both the linear and the angular to get the acceleration. In order to look at just the tension, we have to zoom in on just one of these guys. And I think it's easier to zoom in on this guy because this guy only has the one force on it. So with only the one force, and we already have, based on what we did before, we already have the expression set up where we just have to substitute from our solution to A. We've got mg over m plus 1/2 m. So the usual way of writing this is to combine the terms. All right, all I'm doing from yesterday is, like this was all of the work yesterday to get to here. Once you've done this, you've done the hard part. And now we're just going to take this and substitute into the two subsequent things. Pause for a second. Questions? If I change the shape of the pulley to something that is not that, you're still going through the same process. You're still starting with, here, let's do orange. We're still doing that guy and that guy and that guy and that guy and that guy, but that's what changes, right? The orange underlined things are all basically the same as they are now. The only guy that changes is the pink box. Because if you change the shape of the pulley, then you're changing the rotational inertia, and then that's going to change things later on, but your starting point's still the same. All right, part D that I didn't get to because I ran out of board space and time yesterday. How fast is the block going when it smacks into the floor? And there are two ways to look at this. That's why I have a dashed line down the middle here. Two different ways to look at it, but they should give the same result. All right, so if I drop something, what are the two methods of solution that we can use to figure out how fast it's going when it hits the floor? Kinematics or energy. All right, we can do kinematics because we've got the acceleration now. We already did dynamics. So you got to keep in mind, it's not just kinematics, it's dynamics kinematics. But we already did the dynamics part. Or work energy. All right, so for kinematics, so this guy is, I'm not writing that whole thing there from part A. The acceleration from part A, this guy is y, this guy is 0, that guy's a question mark, and now we are all here. So don't care about time. So VF squared equals VO squared plus 2AS. So that's going to be the square root of 2 times that thing. 2mgy over m plus 1/2 m. Now, once you've done all the dynamics and you get to that, that's probably the most straightforward way to do it. All right, work energy. At the beginning, we've got potential energy. And then at the end, well, wait a second here. At the end, this guy's translating. Oh, I'm off screen. This guy's translating, but this guy's spinning, right? So we're going to have to add these two guys together in the kinetic energies because we have the potential energy gets split between the two kinetic energies. So we're going to have kinetic energy translational, and kinetic energy rotational. All right, who's got the potential energy? Block or pulley or both? Okay, what is the thing that could fall? Just the block. The pulley, we're not dealing with a situation where the axle breaks and the pulley also falls. Not doing that. So just the block can fall. So only the potential energy is from the block. So this is just mgy. And then at the end, we've got 1/2 mv squared and then 1/2 I omega squared. And the 1/2 mv squared is for the block, and the 1/2 I omega squared is for the pulley. So we're going to have to do a couple substitutions here. So this guy is 1/2 mr squared. And the pulley spinning is going to be spinning at omega. And again, this relies on the fact that the string is not going to slip. We're not doing any slippage yet. That will come later. To a limited degree, but it'll show up. All right, let's substitute all these. Oh, keep in mind that this m and this m and that m are not all the same m, so unfortunately the m's do not cancel. So we're going to have mgy equals 1/2 mv squared plus 1/2, that 1/2, and then we have this 1/2, and then we have that guy, and it looks worse than it did, right? A lot worse. Can we clean it up at all? How do we clean this up? Ooh, hey, look at that. There's an r squared, and then in the denominator, there's an r squared. Kill the r squareds. And that guy also. The whole thing dies. And here's a half, and here's a half, and that's missing a half, but I'm prejudiced against fractions, so let's multiply everything by 2, and we'll at least get rid of one of the fractions. And, oh, here's a v squared, and here's a v squared, so let's factor out the v squareds. So we've got 2mgy equals m plus, oh, this is the only thing that survived, 1/2 m v squared. And what I wanted to get was how fast is the block going when it smacks into the floor, which is that v squared thing. So divide and square root. So v equals big square root of this puppy divided by that puppy. Oh, good, I agreed with myself. It's always awkward if I get a different answer. All right, so this one looks like a lot more work right now, doesn't it? But it's everything all in one place. This hides, like, do you notice here, I didn't even write the answer from before because it was too obnoxious. This hides all of that and this, which if I put both of those in here, it would actually be more than this guy, all right? So if they're asking for forces and accelerations, you really should be doing dynamics and maybe some kinematics. If they're asking for speeds, it might be easier to go straight to work and energy. Right? I'm showing them both so that you have at least a model to follow for both, especially when we get to lab and we're going to have things rolling down the hill. And you're going to have to account for, as the thing rolls down the hill, it moves sideways and it rotates. And I'll show you how to deal with that. That's your first look at dealing with that. All right, questions on this? No? Perfectly fine as long as I'm doing the thinking and you're doing just being transcribers. All right, now, your turn. Your turn to do some of the thinking on your own with these 4 carefully selected problems.